Hello, good morning, everyone, and thank you for joining us for Q-Chem's 66th webinar. We're very excited to welcome Elfi Kraka and Marek Freindorf. They will be telling us a little bit about their work with LModeA and sort of their work with extracting chemical information from vibrational spectroscopy data with local vibrational mode theory. Dr. Elfi Kraka is a professor and chair at the Department of Chemistry at Southern Methodist University. She obtained her Doctor Rerum Naturalis in theoretical chemistry from the University of Köln in 1984. And she did her postdoc work at Argonne National Lab. She also began her work as a professor at Göteborg University in 1990, where she stayed until 2005, at which point she moved to the University of the Pacific, where she continued serving as a professor for several years before joining the faculty of SMU in 2009. And her work involves a lot of different things, but includes applications and development of novel methods in artificial intelligence, vibrational spectroscopy, catalysis, materials, and drug design. So she will be our first presenter. And then Marek Freindorf will also be presenting, doing sort of a practical demonstration at the end. He graduated with his MS and PhD with honors in chemistry and a minor in physics from Jagiellonian University in Poland in 1988. He was a faculty member in chemistry department of that university until 2000. He worked as a postdoc at the University of Bonn in Germany, and then University of Buffalo in New York, and then University of Louisville in Kentucky. And from 2011 onwards, he has held a research professor position in the chemistry department of SMU also. He's authored about 60 papers involving theoretical molecular spectroscopy, computations of homogeneous catalysis with transition metals, and QMMM calculations of DNA and protein active sites. So thanks to both of you for sort of being willing to tell us a little bit about your work, and I'm really looking forward to hearing more about what y'all have done. So thanks, and I will go ahead and hand it over to Elfi now. Here we go. You should be able to share your screen now, whenever you're ready.
Yeah, so let's see, how can I do that? Do you see my screen? Because, so can you see my screen? Oh, here we go. Can you see my PowerPoint presentation now? I assume yes. So then I would like to thank Shannon for her kind introduction. And as she said, I would like to share with you how we decode information from vibrational spectroscopy. Here you see the outline of the webinar. First, I will give you some background of local vibrational mode theory and an overview of some recent applications. And then in the second part, Marek takes over and shows you how this works in practice. And then in part 3, hopefully there are some questions and comments from the audience. First, I would like to give you some background. The Computation and Theoretical Chemistry group CATCO was originally formed in the 80s at the University of Cologne in Germany by late Dieter Kramer, where the group developed its major tool, the program package Cologne. In 1990, we moved to Sweden, then relocated to California, and since 2009, SMU is our home. I also should mention that since 2017, SMU offers a specific PhD degree in theoretical and computational chemistry, which guarantees a PhD degree in 4 years. Here is where you will find us in Dallas on the beautiful SMU campus. And as Shannon already mentioned, we have a broad interest in application of methods and their development. But today, I will focus on the local vibrational mode theory. Here is the current group, which does all this nice research. Now let's start with the chemical bond, which is at the heart of chemistry, but many things a chemist deals with on a daily basis, a chemical bond cannot be measured. It's just a concept. On the other hand, vibrational spectroscopy offers detailed information on the electronic structure of a molecule and its chemical bonds. Because vibrational frequencies can be measured, they also can be calculated. We can even visualize in the normal modes how the atoms move during a vibration. So it is obvious that one wants to use vibrational frequencies and related force constants as a measure of bond strength. But here you see already a question mark. How do we get this information? Well, if you perform, for example, a Q-Chem calculation, you can do a normal mode analysis, and then what you get is you get normal mode coordinates Q, a diagonal force constant matrix Q, and normal mode vibrational frequencies. That is all very routine, so that means you don't have to bother about. However, you should bother about something which already Wilson pointed out in 1941, namely the normal mode coordinates are generally a sum over several internal or Cartesian coordinates. And that leads to the fact that the normal modes are generally delocalized, as you see here in this picture of adenine-thymine base pairs. So that means there is limited use of normal mode frequencies and force constants as a bond strength measure. What we actually need is we need local vibrational modes and related force constants for that purpose. This was already discovered in 1998 by Concoli Kramer, who went back to the original Euler-Lagrange equations of vibrational spectroscopy. And then they had the idea, we take an atomic fragment, could be 2 atoms form a bond or a larger fragment, and then we only keep the masses of the atoms involved in this fragment, solve the Euler-Lagrange equation, and then we get local vibrational modes. And here you see as an illustration how this looks like for a CCl bond. Definitely, if you would take the normal stretching mode, this is not a good bond strength measure because there's a lot of coupling. But here you see the pure local stretching mode. So in summary, local modes can be obtained from force constant matrix K and normal modes vectors D in internal coordinates, again available in the Q-Chem output. Very important, the local mode force constants directly reflect the strength of a bond, and we can use all sorts of different coordinates as long as we are able to fulfill the Wilson-G formalism, which I will show you. The main features, to summarize, are local vibrational modes can be applied to single molecules in gas phase solution or even in an enzyme. And if time allows, I will also show you we recently have expanded this to periodic systems and crystals. Very important that we could prove there is an intrinsic bond strength directly be referable to the local stretching force constants. And our local modes are physically based because there is a one-to-one unique relationship between normal and local modes, which has already led to a total new way of analyzing vibrational spectra. Here you see our local modes. They are in total agreement with what you can measure, for example, via overtones or isotopes. But of course, here the warning, these experimental techniques are only of limited use. I also should mention that the term local mode in solid state physics has a totally different meaning. It mostly refers there to crystal vibrations involving defects. And here you have another definition. So we are using this in a very specific way. Over the past 10 years, we have applied local mode theory in order to analyze covalent bonding, weak chemical interactions. We have also looked at a number of different other concepts. If you are interested in this work, please go to our webpage. What I will do now in the following, I will just give you a taste of what you can do. Let's start with metal ligand bonding, which stretches from materials to biochemistry. So in particular, metal ligand bonding in proteins. For example, there was an open question, how does the anazone iron porphyrin complex bind to myoglobin? Does it bind in this way via the distal form, or here does it bind in the other way, which you cannot detect if you just do an X-ray because you don't get information on hydrogen bonds. And you see here, we could solve this problem because in the distal form, we have a stronger hydrogen bond and we also have a stronger iron-nitrogen bond. We also were able to address the question whether, for example, in carbomyoglobin, carboxymyoglobin, there is an inverse relationship between the strength of the iron carbon and the CO bond, which was assumed. But here, as you see in these plots, yes, we quantitatively could prove this. And we also give some more information, namely that especially hydrogen bonding plays a dominant role in addition. Now let's turn to sandwich complexes, which also have attracted a lot of attention. And here I will show you that our local modes analysis can be extended to different bond strength parameters. As you see here, for such systems, it may not be good to calculate the strength between all metal carbon bonds and then average. We would like to have a direct measure of these interactions. And we did this in order to succeed. We move the ring into the Kramer-Popel mean ring plane, and then we use these vibrations shown here as bond strength measure. We are currently applying this to a set of almost 100 different metal pi interactions. And just to give you first results, what can we do with it? If we start from ferrocene, then with our analysis, we can directly tell you here, if you want to have a stronger interaction reflected by a larger force constant, we can achieve this by putting fluorine ions in one ring. If you want, on the other hand, have to have a weaker interaction, then the best way to achieve this is that you substitute the carbon atoms in the ring with phosphorus atoms. Recently, we also got interested in uranium, which has attracted a lot of attention. We are interested in the rich coordination chemistry. So far, uranium oxidation states from 3 to 6 have been reported, and just recently, uranium-2 has been added to the list. And here you see what rich coordination chemistry is covered by uranium compounds. And just briefly mention this topic here, which already has led to a lot of controversy in the field. So the question is there really a UN triple bond? And why should we bother about this? Because these complexes here, the uranium nitride complexes, they are suggested as future player for ceramic fuel in nuclear reactors, because they are much easier to handle and they also can be easy to be reprocessed for further use. And here you see our result. We definitely could prove, yes, there is such a uranium triple bond. Now let's move to a totally other spectrum. So we have uranium, radioactive material. What can we do in the sector of drug design? Our attention was recently raised by covalent binder drugs, where the drug directly forms a bond with the protein target. And as you can imagine, here you need a quantum chemically based measure of bond strength, and you can no longer get along with molecular mechanics descriptions. One pilot project we just published is in the interesting field of phototherapy. What does it mean? So the drug is transported to the tumor cell and then it becomes activated after visible light irradiation. So far, platinum has been used, but recently the community is turning to ruthenium drugs because they are easier to uptake and it seems that they have less toxic side effects. So, for example, here in this study, what has been done experimentally, a whole set of such drugs have been investigated, where you see you have here the complex, ruthenium complex. It is then excited to a transition state. Then the drug is released, and from the transition state, the complex relaxes into the singlet state. And in order to measure the efficiency, experimentalists then measure the quantum yields for the subsequent attachment of a water molecule. Of course, the question is, does this indirect bond strength measure really work? Does it reflect that the ruthenium and C bond is the bond determine the biological activity? So what we did was we investigated a whole series of synthetically compounds. Here you see ones which had a lower quantum yield, here ones with a higher quantum yield, and I also show you what we then finally suggested. And very interesting, performing the local mode analysis, we could show that as a matter of fact, the compounds which show a higher quantum yield have a stronger ruthenium bond. So obviously the ruthenium nitrogen bond strength cannot determine the biological activity, but we figured it out. It's this, the change from a 6 coordination state to a 5 coordination state which kicks out the drug. And this is, of course, a very important finding for the drug designer community. Another pilot project concerns COVID. Recently, one thinks about alpha-ketoamide inhibitors, which are supposed to form a bond with the viral cysteine protease, and in this way blocking the replication of the virus. And here you see some first results which just got published. Indeed, there is a formation of a CS bond, and now with the local mode analysis, we are in a position that we now can model what do we have to do in order to get this bond as strong as possible. Now let's move into the other very exciting thing we can do with our local mode analysis. We can take a look at vibrational spectra and try to get more information out of this. So we have two tools, and I will show you this just for the water molecule. My colleague Marek will show you later more how you can do that. So for example, if we have water, we can decompose the normal modes into local mode contributions, and obvious, both stretchings show 50% of OH normal mode, and here you have the bending. And here you see also the adiabatic connection scheme, starting from the local modes, slowly activating the masses of the atoms which were not used in a certain local vibration. Then you see you have a smooth transition of the local modes into the corresponding normal modes. We also can use this as assessment. For example, if you use 3 distances in the water molecule, then you see again they transform into the asymmetric and symmetric stretching and the bending. If you supply more coordinates, what we call a redundant set, then you will nicely see that one of the local modes which doesn't have a partner as normal mode drops to 0. And if you do something which is physically not meaningful, this will also reflect in this ACS. Now let's apply this to the vibrational Stark effect, which refers to the sensitivity of a spectroscopic transition applied to an electric field. If the field is weak, like we have in proteins, there is a linear relationship. So what you have to do is you have to stick a probe to one protein, and then you attach the second protein, and then by the frequency shift of this vibration, you can measure the field strength. And when we got interested in this project, we were very surprised that these probes are frequently used, but it wasn't checked whether these probe bonds are really local modes, because otherwise the whole concept doesn't work. So what we do in this CNM procedure, we decompose each local mode into local mode contributions via the overlap, and then we get a performance score. So that means if the normal mode is 100% localized, we get here 100, and definitely for a good vibrational Stark probe, we should get here numbers in the hundreds. So far we have analyzed about 100 such probes, and I will just give you a flavor. This is a very popular CN probe, and here when you do the decomposition of all normal modes into local modes, then you see definitely that is a good probe, because here you see the CN vibration is 93% localized. And here you have, as a second proof, the adiabatic connection scheme. Now, let's look at another probe where we have a silicon-nitrogen probe bond. Again, a very good probe, but what happens if you would use a phosphorus atom instead and have a silicon phosphorus bond? Not a good probe, because now you see it's no longer localized. And so this is a very powerful tool, so that experimentalists, before starting a synthesis, can directly check whether something is meaningful or not. Now let's look at vibrational coupling in DNA base pairs. I already mentioned that. Based on 2D IR spectroscopy, there is the idea that you have a lot of bonds coupling in these base pairs in the fingerprint region, which makes the analysis of the vibrational spectra very difficult. And we wanted to quantify this. And here let's take a look at the AT base pair again, which I showed you in the beginning. Just looking at the normal mode at 1599, there we see indeed we have here a contribution from this CO bond, and then we have stronger contributions also from these bonds, which you find in the thymidine partner. Now let's take a look at the CT bond, a base pair. What you see here is, for example, looking at 1641, we indeed find a coupling here from the CO bond and from that CC bond, but we don't find any contribution from this CO bond here. This is rather very localized. So again, this should show you that this is a very powerful tool to give the experimentalists information on how the normal modes are composed of local mode contributions. And now finally, I will move into something which we recently did. So the question is, we have analyzed now the bonding in gas phase, in liquids, in the enzyme. Can we also use this in order to get an idea about the bond strength in periodic systems? Of course, here one has to consider a couple of things. As you all know, in a single molecule, we always have 3n-6 or 3n-5 normal modes. In a periodic system, this strongly depends on the periodicity, whether we have 1D, 2D, or 3D. One also has to be very careful. If you do phonon spectroscopy, only when you are at a gamma point, you get something which can be measured. So therefore, what we have done is we have then developed local vibrational mode theory determined at the gamma point. From a computational point of view, also very important, you only need the optimized lattice structure of the system and its Hessian for the primitive cell. And very important, we can now compare chemical bonding in a molecule and see what happens, for example, in the transition to a crystal. One application I would like to discuss in the following, the local mode analysis to the hydrogen bond network in ices. If you think about ice, of course, you have hydrogen bonds. What generally is used as a strength is the lattice energy, but energies are a cumulative property. So we wanted to bring a more individual measure, namely individual hydrogen bond strengths. So far, 19 different ice structures have been experimentally confirmed. 51 additional are predicted. So it would be very important to understand the hydrogen bond strength in these systems. And as you can imagine, there is a difference in hydrogen bond strength determined by the environment in the crystal. So we analyzed local vibrational modes for 16 ice polymorphs, which are stable under ambient to elevated pressures. And here you see the results. And as you already can see from these crystal structures, they are topologically quite different. To highlight some results, what we found is that ices, which are found on the Earth, the hexagonal form, they are held together by very strong hydrogen bonds, as you see here. Then there are other ices, which are, for example, found in the interior of our Earth. They have weak hydrogen bonds. And then you find hydrogen bonds which are in between. Interesting, you can see some of the ice forms, they have a very narrow range of different hydrogen bond lengths and strengths. Others have a broad range, and the same what we see here for the hydrogen bond acceptor, we also find for the donor. Also very interesting, the strongest hydrogen bonds you find where the bond angle is 180 degrees. And so what can we do with this? We took a look at the water ice phase diagram, and there you see in the region where you have low pressure, like here on our Earth, you need strong hydrogen bonds for getting this network stabilized. In the interior of the Earth, where we find weak hydrogen bonds, you need a lot of pressure. And we suggest to use these local modes in order to predict what pressure a new ice form should be exposed to. And in this way, we will help the experimentalist before doing the synthesis to get information about how this can be realized. With that, I'm almost at the end of my presentation. Here you see the flow chart of the local mode program. We have currently interfaces to about 20 quantum chemical packages. Of course, Q-Chem is included. So what you need to store are the Cartesian coordinates, information about the Hessian, and then of course you have to define the local modes. This will be shown by Marek. I would like to acknowledge support by the National Science Foundation and other foundations to sponsor this research, and definitely this research would not be able with the strong support of SMU's High Performance Computer Center. And now I would like that we turn over to part 2, and my colleague Marek will show you now how the input for such an analysis works. Thank you very much.
My name is Marek Freindorf, and in this short presentation, I will show you how to practically use our program. LModeA program is written, as Elfi mentioned, in Fortran 90, and it doesn't require any graphics. It means it can be installed on any operation system with this compiler. The program is distributed in a source code, so anybody can actually very simply install this program locally. And the program takes the text input file, and it generates the text output file, and here you can see an example how the program can be executed on a Linux operating system. And this is the snapshot of the input file for LModeA. It has 3 general sections. The first section, control section, describes the technical details of the calculations. Then the QC data section describes the name of the formatted checkpoint file from the frequency calculations, which should be done before using LModeA. And the last section describes the local modes. In this particular example, I am using Q-Chem program, which is one of 20 quantum chemical programs for which we tested our LModeA. And after frequency calculations, the formatted checkpoint file was saved with this name, with the same directory as the input file. And in the definition of local modes, the user should provide numbers of atoms, 2 numbers for the bonds, 3 numbers for the angles, and 3 numbers for dihedral angles. That's the standard local modes. And I will be also talking about different non-standard local modes which LModeA provides. And important thing is that the frequency calculation should be done for a stationary point on the potential energy surface. It means a minimum on the potential energy surface, or a transition state, a saddle point only. This is a snapshot from the output file from LModeA. It shows the geometrical parameters of local modes, like bond lengths, which are expressed in angstroms, bond angles expressed in degrees, local mode force constants, which for stretchings are expressed in millidin per angstrom. For bendings, they are expressed in millidin angstrom divided by radians square. And at the end, you can see local mode frequency expressed in wave numbers. In this example, program calculates 2 components of degenerated local vibrations, which are bending vibrations of this carbon dioxide. And those 2 components are labeled as -1, -2 here at the end of this definition. And in the output, you can see first the analysis of normal mode, 2 degenerated normal vibrations, and then a snapshot from the end of the output file from local mode, showing the degenerated values, the same values for degenerated components of this local vibration. In the example number 3, this example actually presents how our program can be used to calculate local modes based on experimental frequencies. But first, the user should run theoretical calculation of frequency of molecular vibrations for the same molecular system using any level of theory. And but there is another section which is required in this input, in which the user should specify the frequencies, the experimental frequencies. And what is important, the order of those experimental frequencies should be the same as order of theoretical frequencies. In the output file, there will be a table showing the experimental frequencies, the theoretical frequencies and the correction, and values of the local mode parameters which are based on experimental frequencies. In the example number 4, program calculates local modes in clusters. In this example, I am interested in the interaction between the argon atom and the benzene molecule. And in the input file, I specify 2 local modes. The first is which describes the interaction between the argon atom and the ring formed only from carbons. And the second definition, the second local mode, involves all atoms of benzene. As you can see from the results, the force constant for both local modes is the same. However, the frequencies are different because the masses are different. In the example number 5, program calculates the adiabatic connection scheme and the bar diagram. And the user should provide in the control section 2 additional keywords. The first keyword is needed to generate a separate text file with the extension DAT for adiabatic connection scheme, and the second keyword with a default value 50 is needed in a situation where there are some numerical instabilities. User can change this number. In the local mode definition section, the user should provide the exact 3n-6 non-redundant local modes. The program checks redundancy. If there is a redundancy between the modes, then the analysis is not completed. In the output file, the program prints out the decomposition of each normal mode into a local mode percentage. And for example, for this normal mode of symmetry double prime, this particular normal mode has 50% of local stretching, local vibration number 7 and number 8. And those data can be graphically visualized in a bar diagram. And for example, the normal mode of this frequency has 100% of the stretching vibration between oxygen and this hydrogen. This example also generates a text file with this name, which includes frequencies of normal and local modes for different values of parameter lambda, and this scaling parameter lambda. If the lambda is 0, then those frequencies correspond to local mode vibrations, and if the lambda is 1, those frequencies correspond to normal mode vibrations. You can see how they are changed. In the example number 6, the program calculates a non-redundant set of modes, including a motion between monomers in a dimer. So I am here interested in a specific interaction between this titanium atom and this open ring, actually in a pi system of this open ring. And this example has 2 steps. In the first step, the program generates all redundant local modes, 177 of them, with a condition that this particular part of the cluster, it's a ring, even it's an open ring, and the numbering in this ring should be provided in clockwise or anti-clockwise fashion. And in the second job, the user should specify 3 modes describing the move of atom number 5 relative to the geometric center of the ring in direction of x, y, and z. So these are the definitions three definitions of those three components of this interaction, and then the user can simply copy and paste the remaining set of local modes, with exception without actually local modes involving the titanium atom. And in the output file, you will see that from 60 parameters which are provided in the input file, the program extracted only 33, and the first three of them are those important for which the analysis can be performed. In the example number 7, the program calculates the pyramidalization local modes, and this is the example for this particular molecule. And here it is a definition of a pyramidalization local mode involving a move of the carbon atom in direction of the fluorine atom, where the carbon atom and three hydrogen atoms form a pyramid. And in a similar way, here is another local mode definition where the carbon is moving in direction of that hydrogen. And you can see that those two different local modes, they have different parameters. And the last example, it's an example how our program can calculate Packering local modes, which are based on Packering coordinates originally developed by Popul and Kremer many years ago. And for this is the example for cyclohexane, which can exist in two conformers, chair conformational form or both, and in conformers in between them. And for 6-member ring, there are 4 Packering local modes, which are shown right here. And 2 of them are important. Actually, Q2 describes the amplitude of Packering motion, which is displacements, which are displacements of all carbon atoms from planarity, and phi2, which is a phase of Packering motion, which describes the character of this movement. And you can see here results of this analysis. And this is the last example.
Yeah, thank you so much for the talk. And really quickly, so you can post questions in the chat over here on the side. Looks like we've already got a couple of questions. So first one is from Peter Berger. He says, very nice talk. And Elfi, have you looked into methane calthrates, so water methane clusters at all?
Not yet, but this would be a very interesting system to check.
Awesome, thanks. And then we've got another question, which is, if in an experiment there is a split between symmetric and anti-symmetric stretches, like in the water case, would the local mode analysis give 2 identical OH frequencies and then not be able to capture the split?
So maybe I can answer that. If you think about back what we had in the water molecule, the local modes, they don't have any symmetry. So if we start with the local modes for the water molecule, we have 2 identical OH stretches. And we get this transformed into symmetric and asymmetric modes if we transform them via the asymmetric connection scheme into the normal modes. So that is the underlying idea.
Okay, Cool, that makes sense. Thanks. And I'll check on the forum real quick to, oh wait, we've got another one in the chat. Is it possible to use local mode analysis to get information of a given reaction coordinate at the transition state region?
Yes, I mean, if you have a transition state, then you can analyze the local modes at the transition state. If you are away from the transition state, let's say you are following the IRC, then of course you have to be careful that maybe you have more than one imaginary frequency because you are not at a local minimum. And then you have to project out this. So what can happen is we did a lot of testing. If you would, for example, plot the force constants along the direction path, it could be that if the direction of one of these imaginary modes is exactly in the direction of this force constant, then things blow up. So therefore, the recommendation is to restrict the local mode analysis to the stationary points.
Okay. Okay, thank you. So then we've got another question also, which is, could you please talk about the relationship between LModeA program and the LModeA nano program? So like similarities and differences.
Mm-hmm. So the LModeA program was first designed for gas phase, then liquids and enzymes. And you can do solid states with LModeA as it is. The only problem is it requires a lot of manual work because when you have a unit cell, you have to give information about the lattice parameters and so forth. So the LModeA Nano is a plug-in which helps you to prepare the input for this purpose. But of course, if you don't want to work with this plug-in, you can also do just the regular LModeA, but then of course, it's a lot of manual work. Does this answer the question?
I think it does. If the person who's asked this has any follow-up questions, then definitely feel free to post them in the chat. And then we've got another question, which is, in the investigation of the vibrational Stark probes, have you checked the case of the carbonyl group? He's curious what the result looks like.
Yeah, we did carbonyl, we did CN, we checked about 100 different probes, and if you are interested, everything is mentioned in this article we published in Sensors, and there's also a supporting information with all these 100 molecules.
Okay, awesome, thank you. So yeah, I don't know if y'all caught the Sensors article, but we've got a Q-Chem webinar post on our forum. So if anyone missed that, we can I guess we can maybe post an article link or something on there. So
yeah, I mean,
yeah.
The easiest way would be just, if you are interested in a special topic, just send me an email. Or the other way is just go to our CATCO page to publications, and then you will find all these publications.
Yes, thank you. And then additionally, we do, like I said, we've got a post on the Q-Chem forum where if anyone has any, I don't see any additional questions in the chat, but if any of our members of our audience have additional questions that they would like to ask, they're welcome to post them on the forum. So, and I'll forward them to you, I guess. So, all right. Well, thank you so much. That was a really cool talk, and it's really interesting to see the sort of analysis that you can get out of these sorts of calculations and the sort of information that you can obtain. Yeah, thank you so much for talking about your work.
Yeah, and maybe you should mention again, so if someone is interested just to do the local mode analysis, please send either Marek or me an email, and then we will send you the package, the source code, and also tutorial examples so that you can try this on your own.
Yes, it's definitely good to be able to have access to the source code and all of the, you know.
And I also should mention, I mean, whenever you have done the frequency calculation, which of course is the most important part and the most expensive part, then basically the local mode analysis can be almost done for free. So that means there is this additional information around just waiting to be decoded.
Yeah, so it's not, you know, it's not a ton of expense on top of the vibrational calculation. It's just, you know, it's just a matter of extracting that information that already exists. Yes. So anyway, it's very cool, and it's very exciting work. So thank you so much for sharing. And yeah, as Elfi said, please feel free to, you know, contact us with questions, or you know, contact her or Marek for information about like the source code and things like that. And yes, thank you so much for to all of you for your attention. Elfi and Marek, if you guys want to say anything, now is the time. But yeah.
Yeah, I would just like to thank everybody in the audience, and of course also Shannon, for making this happen. And we are really excited about sharing this with the community. And also, of course, getting feedback, because whenever you develop a program, there might be things which still don't work and other things which work well. So I think just having this connection with the broader community will bring us to the next level. And this is, I think, what we really want to get out of this webinar.
Yeah, absolutely.
Help sharing us this information and applying it to their projects.
Yeah, it's really cool and exciting work. And I know, like, as a Q-Chem person, it's definitely useful to have that sort of feedback loop with people who are actually using our software. So anyway, but thank you so much to both of you for presenting your work. And I look forward to seeing everyone at the next webinar. Thanks so much. Have a great day.
Thanks so much. Thank you. Bye-bye.
Bye-bye.